Mudrocks clays, which are sheet silicates the size of colloidal particles, viruses, or the particles of smoke from a cigarette, are the most abundant minerals on the surface of the earth. Clays cover about 75% of the land surface and blanket most of the deep seafloor in pelagic oozes. Mudrocks are by far the most abundant class of sedimentary rock, making up between 50% and 80% of Earth's total sedimentary rock shell. By any measure, clays and mudrocks are among the most important materials on the surface, and that should be reason enough to study them. The term mudrock refers to all siliciclastic sedimentary rocks composed predominantly of silt-sized, 1/16 to 1/256 or 0.0625 to 0.0039 mm or 4 to 8 phi, and clay-sized. Mudrock includes two lithologies, in which one of these size ranges predominates siltstone, with 50% or more silt-sized material, and claystone, with 50% or more clay-sized material, as well as lithologies that are a mix of the two. Mudstone is indurated mud, which is a mixture of silt with between 1/3 and 2/3 clay. Shale is any mudrock that exhibits lamination or fissility or both. Argillite is mudrock that has been subjected to low-grade metamorphism. Mudrocks are also referred to as pelites, pelitic sedimentary rocks, from the Greek for mud, lutites, from the Latin for mud, and argillaceous sedimentary rocks. Considering the great importance and abundance of these rocks, it is surprising that there are so few published mudrock studies and so few specialists who work on mudrocks. This disparity reflects the difficulties of studying these rocks and the ambiguities of the resulting data. What are the obstacles to understanding this rock type? Even though mudrocks are the dominant rocks by volume, they are typically revolt/uprising, well exposed. In most climates, mudrocks weather deeply to form valleys or lowlands with few or no outcrops. In addition, mineral composition and texture cannot be studied easily in the field or laboratory. The mineralogy and texture of silt-sized clasts can be determined only in a rudimentary fashion with a petrographic microscope, and this method is of no use for clay-sized materials. Even X-ray diffraction methods able to identify individual clay minerals provide only crude estimates of clay mineral abundance. Grain size data obtained using sedimentation tubes have produced few meaningful conclusions. And the sedimentary structures in mudrocks are difficult to see and are of limited use in interpretation. In addition to the practical problems, there are other, more subtle reasons for the comparative neglect of mudrocks. Sedimentary research has long been driven by economic motives, especially the needs of the petroleum industry, and for a long time, mudrocks were considered the uninteresting source rock from which the organics had migrated away. Not the profitable reservoir rock where hydrocarbons accumulated, these are usually sandstones or limestones. When the possibility of extracting hydrocarbons from oil shale emerged in the 1970s, there was a sudden expansion of mudrock research. Then the price of oil collapsed, and with it, oil shale research, exploration, and investment also declined. Another historical factor is the fact that most marine mudrocks are deposited in the deep ocean, which makes them extremely hard for land-based geologists to study. Because very little was known about them, the understanding of deep marine shales exposed on land was also very limited. When various oceanographic vessels began deep-sea coring in the 1950s and 1960s, and when the deep-sea drilling project began routinely drilling cores in the ocean floor around the world in the 1970s and 1980s, the interest in the clays on the ocean floor suddenly increased. Despite these problems, recent improvements in analytical and interpretive techniques permit sedimentary geologists to cope better with mudrocks. Texture: there is no general agreement about the best way to categorize mudrock types based on the proportion of sand, silt, and clay. Boggs, 1992, suggested that the typical mudrock ranges from 80% silt, 17% clay, and 3% sand, that is 2 parts silt and 1 part clay. In any case, there is less textural variation among mudrocks than among coarser-grained siliciclastics. The various mechanisms that entrain, transport, and deposit silt and fragments finer than silt evidently do not discriminate among them well. No diagnostic textural fingerprints can be used to match grain size distribution with transporting agency. Clasts in mudrocks tend to be more angular and less spherical. This is probably a consequence of both mineralogy and size. Silt, and especially clay-sized material, consist mainly of flaky fine micas and clay minerals, not quartz, feldspar, and rock fragments. These materials are carried by weak currents that cause little abrasion. 1. Well-developed facility in the shale note hand lens for scale. 2. Terrestrial mudrocks can often be distinguished from marine shales by evidences of subaerial exposure. 1. 2. Many mudrocks exhibit a preferred fabric caused by the parallel alignment of flat, flake-shaped micas and clays. This fabric is expressed as fissility, the tendency of mudrock to part or split along thin, closely spaced parallel surfaces. Shale is a general term used to refer to any mudrock possessing fissility. The thickness of the sheets, 10 mm, is termed as slabby. Although such terms can be used to describe shale in the field, they have dubious, uncertain/unsure, genetic implications. Composition, quartz and feldspar are as important in mudrock as they are in sandstone. Fine-grained micas and clay minerals replace the rock fragment component. Boggs, 1992, defines a typical shale contains 30% quartz, 10% feldspar, and 50% clay minerals, or fine micas, 10% is cement, mainly carbonate or iron oxide. Courses in mineralogy rarely discuss the clay minerals in much detail, so we will review the important ones found in most modern and ancient muds. Because clays are very complex chemically and mineralogically, however, the simplified discussion below ignores much of the variability and most of the less common clay types found in the real world. Clays are phyllosilicates, minerals that consist of tightly bonded sheets of silicate tetrahedra, T-sheets, internally linked together with shared corner oxygen anions. Oxygen. Silicon. Tetrahedral. Silicon oxygen tetrahedral layers sheet. Octahedral. Al, Ca, Mg, Fe. Aluminum hydroxyl octahedral layers sheet. O. 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 Attached to these tetrahedral sheets and mutually sharing certain components with them are octahedral sheets, O sheets. They are composed of hydroxyl, O, anions arranged around cations such as calcium, aluminum, and magnesium. As a separate mineral made of aluminum hydroxide, this combination is known as gibbsite, so the octahedral layer is sometimes called the gibbsite-like sheet. From these two basic building blocks, plus additional cations and anions, a great variety of clay minerals can be constructed. Most are composed of sandwiches of tetrahedral or octahedral sheets, which repeat over and over again. Various cations and anions are found between the sandwiches, resulting in much chemical variability. 1. Kaolinite, Kandite group. The simplest arrangement characterizes the Kandite group of clays, most commonly represented by the mineral kaolinite, whose name is often used to refer to the Kandite group. Kaolinite is composed of an open-faced sandwich of one tetrahedral sheet and one octahedral sheet in each repeating layer, or a 1-1 arrangement. The layers are tightly bonded together, with only hydrogen cations between them, so their structure is H plus, O, T, H plus T, O, H plus, T, O, H plus, T, O. Unlike most other clays, there is no room for water, hydroxyls, or larger cations between the layers. Consequently, kaolinite clays are chemically and mineralogically simple compared to other clay minerals. Structure of kaolinite, the most common mineral in the Kandite group. Provenance and depositional setting of kaolinite clays. Clay minerals can be produced by the weathering of igneous, metamorphic, or sedimentary rocks. Although igneous rocks initially contain no clay minerals, the feldspars that largely constitute them decompose to clay minerals, especially when the topography is low and the climate warm and humid. Metamorphic rocks also contain feldspars and micas that decompose easily to clay. Weathering of pre-existing sedimentary rocks, especially other mudrocks, generates detritus rich in clay. The particular clay mineral produced is dictated by the extent of decomposition. Extensive alteration generates such clay minerals as kaolinite and gibbsite because interlayer cations such as Na, K, and Ca are completely leached away. Unfortunately, no trace of the original mica or feldspar type survives, so these degraded clay minerals provide no hint of source rock type. In the modern environment, certain clay minerals are associated with specific conditions. As we saw earlier, kaolinite is rich in aluminum but not in other cations. Consequently, it is abundant in areas of prolonged leaching, which concentrates aluminum, particularly if the parent material is also high in aluminum, for example, granites and rhyolites. Such leaching occurs most often in tropical soils with acid conditions and good drainage. The soils of the tropics are often so enriched in aluminum that they become a hard, crusty material known as laterite. Under some conditions, the aluminum concentration is so great that the soil can be mined for aluminum. This is known as bauxite ore. On the deep seafloor, where clays from the land eventually settle out, a predictable pattern can be seen. Kaolinites are most abundant in the tropical belts, especially adjacent to the mouths of major jungle rivers. Kaolinite and gibbsite are the major clay minerals in Mesozoic and Cenozoic rocks. Note that kaolinite is concentrated at the mouths of tropical rivers, because it is produced mainly in tropical soils. Kaolinite, 20%. 2. Elite clay, the most common clays, however, have a three-sheet sandwich structure. In this arrangement, the middle layer is an aluminum hydroxyl octahedral sheet sandwiched between two silicon oxygen tetrahedral sheets, or a 2:1 arrangement of sheets in each layer. This three-component layer is the basic unit, and it is repeated over and over again, with a variety of chemicals in the interlayer spaces. In the notation just used, the structure is T, O, T, cations, T, O, T cations, T, O, T. The differences between 2,1 clays are caused by the variations in these interlayer cations and anions. The simplest 2,1 clays have only potassium cations in the interlayers. We know them as the familiar white mica, muscovite. Muscovite is common in high-grade metamorphic rocks, in granitic and pegmatitic plutonic igneous rocks, and as a diagenetic replacement of feldspars. It is relatively rare, however, in the near-surface conditions where most clays and muds are found. Instead, the stable K-rich 2,1 clay at the surface is elite, the most abundant clay mineral of all. It has about 70%-80% as much potassium as muscovite in the interlayers and has slightly more silicon and less aluminum in other parts of the structure than does muscovite. The potassium cations give the structure strong ionic bonding, so it does not expand readily, and water and T, O, T, K+, T, O, T, K+, T, O, T, K+, T, O, T. Hydroxyls cannot easily percolate through, they are found only on the edges of the sheets unless the structure has been degraded. Provenance and depositional setting of elite clays. Among all 2,1 clay minerals, the K-rich clay elite is by far the most abundant. Today, it is most often found in temperate environments, where there are alternate wet and dry conditions and the soil is neutral or slightly alkaline. The high potassium, an alkali metal, is favored under such conditions. Elites are the most common weathering products of feldspars and micas. Elites are also often produced by the weathering of pre-existing shales, and they are common in deeply buried muds and shales, where they are formed by the transformation of smectite. The rest of the seafloor, especially in temperate regions, is predominantly elite. Biscay, 1965, examined the clay minerals found immediately beneath surface muds off the coast of eastern North. Elite is dominant in temperate latitudes, because it forms in temperate soils. Elite, 40%. America. they are entirely alite. He concluded that Diogenes had altered all clays to alite, erasing the record of climate and latitude. Secular changes in clay mineralogy verify that long-term Diogenes dictates clay mineralogy more than do provenance and climate. Alite and chlorite dominate Paleozoic rocks. Alite and chlorite are more abundant in marine rocks than in non-marine rocks. Unfortunately, clay mineralogy cannot be used as a reliable index of overall depositional setting because many clays re-equilibrate chemically, reacting with both seawater and the fluids contained in the rocks in which they occur. Diogeneses may alter the chemical signature of depositional setting originally registered in clay minerals. 3. Montmorillonites, smectites group. The next class of 2:1 clays is known as smectites. The most familiar of these are called Montmorillonite. A small amount of Mg+2 substitutes for Ai+3 in the gibbsite-like octahedral sheets, creating a small net negative charge, smaller than the charge in alite. To balance this charge, the interlayers are filled mostly with Na+, K+, and Ca+2 cations. Because the charge is smaller than that of alite, water is readily absorbed in the interlayers, making the Montmorillonite structure very expandable in one direction, but the structural integrity of the sheets is maintained. These clays almost double in volume when they absorb water, and they are notorious for expanding so much during oxygen. Al, Mg, Fe. Silicon. Exchangeable cations NH2O. Structure of a smectite clay. Saturation that hill slopes made of Montmorillonite shales, and the houses built on them, can slide during heavy rains. Some sodium smectites, such can expand to 10 times their original volume. Provenance and depositional setting of Montmorillonitic clays. Montmorillonitic smectites are higher in Fe and Mg, so they are commonly found as weathering products of ferromagnesian rocks, such as basalts and gabbros. Although they can form under a variety of conditions, they are particularly abundant in arid areas with alkaline soils. Stagnant water and poor leaching allow the retention of Mg, Ca, and Na cations in their structure, and with their abundant interlayer water, they are favored where extreme wetting and drying occur. Montmorillonite are found throughout the sea bottom but especially in the areas along mid-ocean ridges and near island arcs, where they are produced by the weathering of basalts. Montmorillonite, 50%. Typical clay minerals are rarely composed of a single structural type. Instead, most natural clays are mixed layered, with either regular or random mixtures of alite, Montmorillonite being most common. Another highly expandable clay is known as vermiculite. These clays are familiar from nurseries and greenhouses, where you can buy them by the bag to put in planters. Vermiculites have a complex arrangement of water molecules bonded together in the interlayers, quite similar to the interlayer structure in chlorite, but instead of hydroxyls around a cation, they are water molecules alone. This makes them extremely expandable and capable of absorbing immense amounts of water. Hence, they are commonly used wherever water needs to be absorbed or especially where absorbed water needs to be retained until it is needed. For example, when plant roots run out of easily accessible water in the soil, the vermiculite in the soil traps additional water and helps keep the structure of vermiculite has a complex lattice of water molecules between the layers. Plant alive. Bentonite, another distinctive mudrock that has many important uses is bentonite. Bentonite is a mixture of 2:1 smectites formed from the weathering of volcanic ash that has settled onto the ocean floor. If the clays are more kaolinitic and were formed when volcanic ash degraded in the acidic waters of coal swamps, they are known as tungstines. In addition to clays, bentonites and tungstines contain unaltered igneous materials, such as euhedral biotite flakes, euhedral volcanic quartz, magnetite, euhedral zircon, apatite, zeolites, and a variety of feldspars, especially the volcanic K-feldspar, sonidine. Although most of the volcanic glass shards have long since degraded to clays, occasionally the relict texture of volcanic glass can be seen. Typically, Bentonites are found interbedded with shallow marine limestones or shales. Although bentonite beds up to 15 m thick have been reported, they are seldom more than 0.3 m thick because there are limits on how much glass and volcanic matter can be ejected during a single eruption. The thickness of the bentonite bed and the size of the unaltered fragments decrease logarithmically with distance from the volcanic vent. Volcanic fragments also tend to be graded in size within the bed, showing that they result from a single settling event. Widespread bentonites have been used to determine paleowind directions. Bentonites have their greatest stratigraphic value, however, as a tool for correlation. Because they represent a single, rapid geologic event, they can be used as a time horizon as well as a unique stratigraphic marker in a given stratigraphic correlation setting. Certain bentonites can be traced for hundreds of kilometers and matched up with precise chemical or mineralogical signatures. Unfortunately, most bentonites are too weathered to provide good radioisotopic dates, but occasionally there have been successes. The other importance of bentonite is economic. Thick deposits of bentonite are widely mined commercially for a variety of industrial uses: fuller's earth for decolorizing oils, drilling mud for oil wells, bonding agents to hold together foundry molding sands, and many others. Bentonites are altered volcanic ashes that settle to the sea bottom. A outcrop of Ordovician dike bentonite, crumbly gray layer at chest level, in the middle of a thick sequence of resistant limestones. This immense ashfall, from a volcanic arc source just off the present Atlantic coast, covered the entire eastern United States in the Ordovician. The ash layer was more than a meter thick in the Appalachians and extended as far as Wisconsin and Minnesota. B. The Cretaceous shales of the western interior are punctuated by many ashfalls and bentonites, two white layers in lower center. 4. Chlorites. After kaolinites, ilites, and smectites, the fourth common class of clay minerals is the chlorites. Chlorite is familiar as the green mica that gives greenschist grade metamorphic rocks their color, but they are also common in the clay size range. Like smectites, chlorites have a 2:1. Chlorites have a 2:1 sandwich of tetrahedral, octahedral, tetrahedral components. The interlayer space of these minerals, however, contains a new element, a layer of Mg+2 and Fe+2 surrounded in octahedral, six-fold coordination by hydroxyls, or Mg-Fe(O)6. Because this composition and lattice structure corresponds to the mineral brucite, the layer is called the brucite-like layer. In the notation used earlier, the chlorite structure is T(O)T, brucite, T(O)T, brucite, T(O)T. Fe+2 is usually much less common than Mg+2 in the brucite layer, so chlorites are usually found in areas of magnesium-rich parent rocks, where weathering is not so intense that the iron will be oxidized. Provenance and depositional setting of chlorite clays. Chlorites, which have magnesium and iron in the hydroxyl sheet, are produced by the weathering of ferromagnesian minerals in such rocks. Chlorite, 20%. Chlorite is more common in higher latitudes where chemical weathering is reduced. As basalt and gabbro. Like smectites, they are favored by alkalinity, especially where there is standing water and slightly reducing conditions. The ease of oxidation of the Fe+2 in the hydroxyl sheet means that chlorites can occur only in areas where there is little or no chemical weathering. Today, they are found most often in high-latitude temperate regions. The depositional setting is same as that of the alite clays. 5. Glauconite. There is one important exception that deserves mention: the iron-rich 2:1 clay known as glauconite. Some authors, for example, Odin and Matter, 1981, prefer the term glaucony, although this is not widely used. The Greek word glaukos means blue-green, and its blue-green color is one of the distinctive characteristics of this mineral. The iron-rich chlorite known as chamosite and a variety of other iron-rich clays are often associated with glauconite. Glauconites are often concentrated as spherules and pellets in shallow marine sandstones, giving these rocks a distinctive color, Such rocks are known as green sands. Because glauconites are more often a component of sandstones than of mudrocks, they are typically studied by sandstone petrologists. Unlike just about any other siliciclastics mineral, glauconites are a product, and thus a good indicator, of a specific range of environmental conditions. They form exclusively in agitated, oxidized, normal shallow marine waters. Photograph of glauconite is an iron, rich clay mineral that commonly forms as pellets on the seafloor. A. Typical glauconite pellets, probably of fecal origin. B. Glauconite formed after foraminiferal tests. C. Photomicrograph of glauconite pellets, showing characteristic speckled texture. A. B. C. They are known from water depths of 50 to 200 m, but mostly at the shallow end of that range. However, it appears that the glauconite itself is typically produced under locally reducing conditions, such as when it replaces a decaying fecal pellet or the dead tissue inside a foraminifer shell. Most important, large concentrations of glauconite occur only in shallow shelf environments that are starved of clastic sediment or have very slow sedimentation rates. Odin and Matter, 1981, estimated that, to form, glauconites must reside at the sediment-water interface for 1,000 to 10,000 years, and it takes much longer for highly complex glauconites to develop. Consequently, thick greensand deposits are typically found at the top of shallowing, upward marine sequences and just below unconformities. Apparently, they represent shallow marine surfaces that were exposed to extensive burrowing and diagenesis when the clastic supply ceased. Once formed, glauconites can be redeposited in energetic, well-oxygenated settings, further concentrating some green sands. They can also survive burial in reduced subsurface environments. Most petrologists, however, regard glauconite as a powerful tool for paleoenvironmental reconstruction, because it is practically the only siliciclastic mineral that indicates a specific depositional environment. There is a crude correlation between mudrock color and chemistry. Red to reddish-brown mudrocks are typically ferruginous, black mudrocks are carbonaceous. The mineralogy of the silt-sized component in mudrock is also used for classification. In this method, specimens must be studied in thin section. Mudrock types are characterized as quartzose, feldspathic, chloritic, and micaceous. Mudrocks are also differentiated on the basis of the coarser siliciclastic materials with which they are associated: sandstone, conglomerate, and breccia. Neither of these methods has been very popular. Origin and occurrence: relatively weak transporting currents deposit mudrock. Isolating the site of mudrock accumulation temporally and/or spatially from stronger currents is crucial to the deposition of thick, monotonous mudrock sequences. The depositional setting of a mudrock is not inferred from its texture or composition. Greater reliance is placed on fossil content, sedimentary structures, and the type and origin of sedimentary rocks interbedded with the mudrock. Mudrocks of marine origin include those deposited as abyssal plain sequences far from land. They consist of pelagic materials that slowly settled out of suspension, terrigenous materials transported far out into the ocean basins by weak density currents, and windblown materials from the continents. Some marine mudrocks are transported and deposited by contour currents. These are weak, bottom-hugging currents that flow parallel to the depth contours of the continental slope and rise. Other marine mudrocks are deposited nearer shore in the deeper, more protected parts of continental shelf areas and on the floor of shallow empiric seas, for example, the Mancos and Pierre shales of the Cretaceous Inland Sea of western North America, the Middle Paleozoic Chattanooga-New Albany Shale of the Appalachians. Bands of mudrock commonly occur oceanward from the shore zone, where flakes of fluvially transported materials become attached to one another by flocculation as they enter the more saline ocean. Mud also accumulates on tidal flats. Mudrocks of continental origin include lacustrine deposits and the thick, fine-grained siliciclastics found within meandering river systems. Rivers that flood periodically cause channelized flow to escape the confines of natural levees. The flow spreads quickly and then slows, depositing predominantly finer-grained material across the floodplains. Many streams and rivers draining glaciated regions are choked with rock flour, fine silt produced by glacial grinding. Sediments deposited in the distal or deltaic portion of such systems can be predominantly silty or clayey. Finally, windstorms constantly entrain, transport, abrade, and redeposit fine-grained material as loess across wide portions of the globe. Material from the Sahara Desert is found in the deep Atlantic thousands of kilometers from shore. Proterozoic mudrock facies. Compared to studies of sandstones and limestones, there are relatively few studies of ancient mudrock facies. Most geological literature simply describes such rocks as red shale or black shale and often leaves it at that. In some specific cases, however, there is more information to be gleaned than one would suspect. For example, Schreiber, 1989, studied the mid-Proterozoic Newland Formation from the Belt Supergroup of Montana. He recognized 6 different shale facies based on such features as mechanical strength, carbonate content, silt content, and sedimentary structures. For example, he described siltous shales having silta lenses and laminae, silt-filled desiccation cracks, and lenticular to flazer bedding, all indicators of intertidal conditions. Thus, they appear to be the most near shore of all the shale facies. He described carbonaceous swirl shales having rolled up and folded flakes of microbial mats, as well as alternations of carbonaceous stromatolitic microbial layers and siltous storm layers. These are both indicators of near-shore deposition as well, but just below fair weather wave base where weak storms rip up microbial mats and roll them out to sea. Other shale facies indicate deposition. Storm wave base, or deposition in quiet waters below storm wave base, where the main influences might be gravity flows and silt from occasional storms that is washed farther out to sea. Schreiber's, 1989, shale facies model suggests that mudrocks are much more informative than most geologists think. There is an important caveat, however: these rocks are Proterozoic in age, deposited before the appearance of multicellular animals, especially burrowing animals. Block diagram of the facies patterns, sediment sources, and sedimentary processes in the Precambrian Newland Formation. In the Proterozoic, only stromatolitic microbial mats exerted biological influences on the seafloor. Many of these shale facies may not occur in Cambrian or younger rocks, because the advent of bioturbation and the great variety of marine organisms in and on the sea bottom have changed all the rules. Nevertheless, Schreiber's studies suggest that Phanerozoic mudrocks may yield more information if geologists begin to do the necessary detailed work. Black shales. One of the most distinctive and controversial of all sedimentary rock types is the black shales. Their black color is due to a very high content of unoxidized organic matter. They also contain reduced iron in the form of pyrite and are usually finely laminated, indicating little bioturbation or storm disturbance. Typically, they contain no bottom-dwelling marine organisms, but they may contain planktonic, floating, organisms, such as microfossils or graptolites, or nectonic, swimming, organisms, such as fish and marine reptiles, which sank to the bottom after they died. Occasionally, they contain extraordinary fossils in which even the organic films of the soft tissues are preserved. All these features show that black shales were deposited under reduced, low oxygen conditions. If they are anaerobic, less than 0.1 ml of oxygen per liter of seawater, only bacteria below the wave base of weak storms, but still above average. Tolerant of low oxygen levels can live, and no bottom scavengers can break up the carcasses or stir up the mud. Under dysaerobic conditions, between 0.1 and 1.0 ml oxygen per liter of seawater, organic material accumulates as well, and only a few types of burrowing worms can live. In older literature, you might encounter the term euxinic for these conditions, but it largely has been abandoned in favor of the more precise terms just mentioned. These aspects of black shale are clear. Black shales are famous for the extraordinary preservation of their fossils. Because they are typically anoxic and have no scavengers, even the delicate soft tissues can leave impressions. An unusually well-preserved trilobite, complete with gills and appendages, appears in this X-ray of the Devonian Hunsrück shale of Germany. B. The fish-like reptiles known as ichthyosaurs from the Posidonia shales of Holzmaden, Germany, are often preserved with the body outlines, including the dorsal fin, tail fin, and even stomach contents and newly born young in the birth canal. A. B. As Petitjean put it, that the pyritic black shales were deposited under anaerobic conditions is unquestioned. Whether, however, the basin of accumulation was shallow or deep and whether it was landlocked or freely connected with the sea or even a stagnant area of open sea has been much debated. Influencing the debate has been the choice of which modern analog is used to understand black shale deposition. The dominant model has been the Modem Black Sea, which is a relatively deep basin with a restricted mouth connecting it to the Mediterranean, the Straits of Bosporus and Dardanelles. In Roman times, the Black Sea was known as the Pontus Euxinus, from which the term Euxinic was derived. In Greek, the name means the sea that is hospitable to strangers, a facetious name for a very stormy and dangerous body of water. In the Black Sea, relatively little oxygenated marine or fresh water flows into the basin and it tends to stay near the surface, forming a freshwater lid. Beneath about 150 m, the waters are completely anoxic, contain dissolved H2S, and are completely devoid of animal life. These pyritic black muds of the well-named Black Sea have strongly influenced most research into ancient black shales. More recent research, however, suggests that this deep, restricted basin may not be such a good model for most ancient black shale deposits tend to be found in much more open oceans with no evidence of hundreds of feet of black shale from the Devonian Genesee group, Taganook Falls, Lake Ithaca, New York. Great depth or restricted water flow. In addition, many lines of evidence suggest that not all black shale deposits were necessarily that deep. Many black shales are found interstratified with fossiliferous and burrowed muds, suggesting rapid fluctuations in oxygen content that could not occur in a permanently deep, restricted basin. This is particularly true of the black shales found throughout the western interior seaway of North America in the Cretaceous, but it might even apply to the black shales found in the Cretaceous strata below the modern ocean basins. Other possible modern analogues of oceanic conditions with high organic productivity and little exchange of oxygen with the surface waters have been proposed. It appears that there may be no good modern analog for the great black shale deposits of the past. Indeed, the distribution of black shales in the Phanerozoic further reinforces this point. Most of the famous black shales, such as the Devonian Mississippian Chattanooga-New Albany shales, or the many black shales of the Jurassic and Cretaceous, are known from times when there were unusually high stands of sea level. During these times, the seas flooded the cratons, and black shale accumulated even on the continents. These high sea level stands are correlated with greenhouse atmospheric conditions and a complete lack of polar ice caps. A variety of models have been suggested to account for the production of black shales under these conditions. Most hinge on the fact that under greenhouse conditions, there would be less vigorous deep water circulation than there is today. In the modern oceans, for example, the deep but relatively oxygenated bottom currents are formed by cold, dense waters around the icy poles, particularly the Antarctic bottom water and the North Atlantic deep water. These waters sink and then flow along the ocean bottoms from the poles to the equator. On a greenhouse Earth, there would have been no cold polar waters to sink, and the less vigorous circulation would have allowed the oceans to become stratified with poorly oxygenated waters forming at depth. This is especially true in the equatorial belt, where surface waters are warmer and less dense than those lower in the water column, so that vertical overturn and oxygenation of bottom waters cannot occur. In addition, warmer oceans during greenhouse conditions mean that gases would be less soluble, so that there would be less oxygen uptake by the water. In short, the well-oxygenated oceans of today are probably not a good analog for the warmer, stratified, greenhouse oceans that may have prevailed during the mid-Paleozoic or Cretaceous. Instead, these conditions require special climate modeling methods that use modern examples only as a general guide to the chemical and physical parameters of ancient anoxic oceans.